Okay, so let me go to the GitHub page actually. Last week we finished up talking about Python in general, and this week we're going to begin talking about Python, about NumPy, which is the set of packages available for Python that allow us to do numerical computation, scientific computation, artificial intelligence, and other kinds of numerically complicated operations. So let me go ahead and open up the Jupyter Notebook. All right, I think I have this under Documents, GitHub, Intro Speech Understanding, 2025 Spring, Lecture 5, and let's open Lecture 5 notebook.ipynb. Right, until now, we've been working with the basic functions of Python. We've worked with arrays and tuples and dictionaries. We've worked with strings and real numbers and integers and booleans. We've worked with for loops and while loops. We've defined our own functions and we've worked with modules, and you've seen that a large number of modules are available in the standard library. This week, we're going to be working with numerical packages. Um, these extra modules like NumPy and Matplotlib are the main reason why Python is so popular today. These are the main reason why Python is the toolkit of preference for artificial intelligence and machine learning. And NumPy in particular is a complete implementation of basically a matrix processing language. It's for processing vectors and matrices. And so what I want to start out with today is talking about how NumPy is used to review linear algebra. And then I want to talk about what to do when something is not a matrix or vector, but just an array of numbers. NumPy has computationally efficient methods for dealing with arrays of numbers and with linear algebra. And then I want to define a few of the special arrays that you can use in NumPy. And then after we understand NumPy, so we understand how to do numerical computation in Python, then I want to talk about plotting. Plotting is usually done using Matplotlib. Let me open up these web pages. The NumPy is described in this web page, and if you want basic documentation, the documentation is here, or if you want to start to learn how to use NumPy, you can go to this page in order to learn um, the quick start tutorial. And all of this tutorial has a lot of information that will help you to learn how to use NumPy in case the material that I cover in the course in the lecture today is not enough. Similarly, Matplotlib is Python's package for creating a wide variety of different plots. So just let's see if we have a variety of different plots here that we can see. Um, hmm. Do we have demos? Plot types. Here we go. So you can create line plots, scatter plots, bar plots, stacked plots, fill between plots, stem plots, stairs and values. You can create histograms, box plots for statistical analysis, plots with error bars, 2D histograms, plots of events, violin plots in case you want to plot sort of the outliers and the standard deviation. You can show images, or you can show contour plots of data. You can show quiver plots, which show arrows at every point pointing in a particular direction. You can show streamlines in case you're doing a flow, like a fluid dynamic simulation. Um, Contours in a number of, you can do three-dimensional bar plots, three-dimensional stem plots, three-dimensional scatter plots. Um, all of these are available in Matplotlib, and these build on top of NumPy. Most of the arrays that are shown in Matplotlib are NumPy arrays. So this is why I've stacked these two things together today. We're going to learn about the basics of NumPy and the basics of Matplotlib in order to allow you to do just really fundamental linear algebra and scientific computation using Python. So first of all, NumPy. the basic idea of NumPy is that we want to be able to process vectors and matrices efficiently. In NumPy, a vector is, so the basic data type in NumPy is the array, but a one-dimensional array is a vector. And every array in NumPy has a dimension. In this case, it's just a one-dimensional array. So if we put open brackets at the begin and close brackets at the end, notice that this makes this a list. So what I've done here is I've created a list, 1, 2, 3, 4, 5, and then by calling np.array, I turn that list into a NumPy array. I need to import NumPy. So let me import NumPy. If you import NumPy and it's not available on your machine, then you can install it by typing pip install NumPy. But if you're using Anaconda, it should already be installed. Most often, we abbreviate NumPy as NP. And so it's worthwhile to import NumPy as NP. And then when I type np.array, Python knows that I'm talking about a NumPy array. One interesting thing about this np.array call is that it assumes that the object inside is just any sequence of any kind. It can be a list with square brackets, or it can be a tuple using curved parentheses in this way. And notice that by taking this tuple, 1, 2, 3, 4, 5, and passing it to np.array, I turned it into a NumPy array. And let's print is of type, and then let's print the type of X. I can't remember if that's just type or type of. So it's of class numpy.ndArray. So let me first actually define y is equal to the list 1, 2, 3, 4, 5. And then let me print y is of type and then the type of y. And then I will take y and convert it into a NumPy array and then print the result. So you can see that this 1, 2, 3, 4, 5 is of type list. This is a list exactly as we learned about 2 lectures ago. But once we pass it to the function np.array, it converts it to a NumPy array. A NumPy array really looks just exactly like a list for most purposes. Not exactly like. So one feature of a NumPy array is that it can't have arbitrary data types. If I put the string foo as the fourth element in this list, oh, actually it can. I thought that it could only have numerical data types. All right, well, it can have, apparently a NumPy array can have non-numerical data types as well as numerical data types. I didn't realize that. We use it most often, though, to represent vectors, in which case all of the elements will be numbers. The main difference really between X and Y in this case is that as a NumPy array, there are a large number of computationally efficient algorithms that can be called on this NumPy array. So the entire the data structure is redesigned so that rather than for a list, it's very computationally efficient to add extra elements to the list. For an array, it's no longer computationally efficient to add elements to the end, but it's very computationally efficient to perform multiplications, additions, divisions, and other kinds of numerical operations. And so the reason that you want to convert something into a NumPy array usually is because you want to perform numerical operations with computational efficiency. So suppose that we create 2 vectors. One is the vector 0.1, comma, -4, comma, 0.25. Notice that I'm writing my vectors as column vectors in my mathematical notation here, but NumPy actually doesn't care whether it's a column vector or a row vector. And suppose that I define the vector y to be 3, comma, 0.2, comma, 5. And suppose I want to take their dot product. I can write their dot product on the equation line as x transpose y. So this is taking the transpose of this 3 by 1 vector, which makes it a 1 by 3 vector, and multiplying it by this 3 by 1 vector y. And what this dot product notation means is that I want to take the sum of the products of every individual element. So I want to take 0.1 times 3, which is 0.3, minus 4 times 0.2, which is minus 0.8, plus 0.25 times 5, which is plus 1.25. And the result is then 0.75. So this is the kind of mathematical operation that you could do using lists, but it's much more computationally efficient to do this using NumPy arrays. In this case, I create the array 0.1 minus 4.25. I create the array 3.25, and then I compute their dot product. Similarly, matrix vector multiplications are extremely efficient in NumPy. So suppose I take the vector x, and I want to take, actually this should be x transpose y. Let me rewrite it as x transpose y. All right, so I want to take the vector x transpose y and create from it a vector v transpose, which will be a row vector. So I'm going to create a row vector v, and that row vector v I'm going to create by taking the row vector of x and multiplying it by the matrix W. So the matrix W is going to be a 3 by 3 matrix, and I'm going to multiply by that a three-dimensional vector, right? And what that means is that I want to create an output vector whose first element is every element of this vector x multiplied by the first column of W. And the second element of V is every element of x multiplied by the second column of W. And the third element of V is every element of x multiplied by the third column of W, right? So this is V is the vector 0.1 minus 4.25 multiplied, for example, by the matrix 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1. So the first element will be 0.1 minus 4 plus 0.25. The last element will be minus 0.1 plus 4 minus 0.25. And so the resulting vector v will have these three elements, minus 3.65, 0, 3.65. First of all, I need to create the matrix. Matrices in NumPy are created based on sequences of sequences. So let me create a W list, first of all. And then let me convert that W list into a NumPy array. All right. You can see that the list, this list is a list of lists, right? It's a there's a list 1, 0, minus 1, then there's another list 1, 0, minus 1, then there's another list 1, 0, minus 1. And this thing that I've called W list is a list of lists, right? Each of the lists inside it is one row of the matrix W, and the entire list of lists is the matrix W. Once I convert that into a NumPy ND array, NumPy knows that it should print it in this two-dimensional format. So NumPy knows that it should should print it in a format which is more similar to the format that we see for matrices, right? We have this 3 by 3 two-dimensional format that shows how NumPy is interpreting the rows and the columns of this matrix. And we can implement a matrix multiplication by multiplying the vector x by the matrix W. Notice that NumPy doesn't care whether x is a column vector or a row vector. But in my notation, I'm going to go ahead and be careful about this. I'm going to go ahead and, in my mathematical notation, I'll say that x is a column vector always, but NumPy actually doesn't care. NumPy says that if you put a vector x before the matrix W, it assumes that the vector x has as many elements as W has rows. And so when I multiply those two together, I get the resulting vector minus 3.65, 0, 3.65, right? So the the reason for which NumPy was invented was in order to be able to do this kind of linear algebra very computationally efficiently, very fast. Those two operations in particular, the dot product and the matrix multiply, are so useful that NumPy has a shorthand for them. If we use the @ symbol, that means matrix multiply. So if I do the matrix multiply between two vectors, that means that I take their dot product, which is 0.75. If I do the matrix multiply between a vector and a matrix, that means that I take the matrix multiply of those two, which is the vector minus 3.65, comma 0, comma 3.65. All right, so this is the reason then why NumPy was invented. It was invented in order to do these vector and matrix multiplications. However, in many cases, we want to do something, many cases we want to multiply two vectors together, not in the dot product format, but suppose we want to actually multiply every single element together and produce the result. This is called array mathematics. So all of these things are called linear algebra, right? All of the things I've been talking about are called linear algebra or matrix arithmetic. And what I want to talk about now is array mathematics. And array mathematics is where I treat the vector x as simply an array of numbers. I don't pay any attention to its dimension or its size or the number of dimensions that it has. I simply treat it as an array of numbers. So one of the array operations that we can do in NumPy is to simply square it. If we square a matrix, there is a way that you can square a matrix, but NumPy doesn't interpret the square operation as the matrix square. It interprets it instead as an array operation. And this array operation simply takes the square of every element in the array of x. So 0, 1, 2, 3, this array squared is 0, 1, 4, 9. The reason this works is that NumPy interprets the squaring operation, star star 2, as an array operation rather than a matrix operation. This is especially useful if you want to do something like take the cosine of every element in an array. So if I have the array pi times 0, 1, 2, 3, 0, pi, 2 pi, and 3 pi, if I have the elements 0, 1, 2, 3, and I want to multiply them by pi, I can just do multiply np dot pi times x. Remember that this @ symbol means matrix multiplication. The star symbol means array multiplication. So when I take the star symbol and I use that to multiply two arrays, that means that I want the result, which is the product of those two elements multiplied one by another. So let me print out some of these. Print x is, and then x, and then let me print x squared array math is, and then I'll print x squared. And then let me print, let's say, x times pi array math is, and I'll print numpy.pi times x. While I'm at it, let me print what pi is. Pi is a special variable defined in NumPy, and let's find out what it is. And then let's multiply it times x. And then finally, let's print the cosine of x times pi. All right. If I run all of these things, we see that x is 0, 1, 2, 3. So it's the array 0, 1, 2, 3. That's all. It's an array. It's also a vector. But if I square it, this is assumed to be an array operation, and so the result is 0, 1, 4, 9. np.pi is a special constant that's defined in the NumPy package, and so I can print out the value of pi to many digits. Pi is 3.141592653589793, and it goes on all the way out to the precision of your computer. X times pi is 0, followed by pi, followed by 2 pi, followed by 3 pi. So this is array mathematics because I used the @ operation sorry, the star multiplier instead of the at operate multiplier. It would be the same result in this case because pi is a scalar, but if I multiplied by another vector, it would not be the same. And then finally, if I take the cosine of x times pi, I get the cosine of 0, which is 1, the cosine of pi, which is -1, the cosine of 2 pi, which is 1, and the cosine of 3 pi, which is -1, right? So in this way, we can do two different kinds of operations in NumPy. We can do linear algebra operations where we treat the array as a vector or as a matrix, depending on its dimensions. And the linear algebra operations include the dot product and the matrix multiply. Here's the matrix multiply. And these are the shorthand for these are the at symbol. Or if that's not what you want, if you want instead is to apply a particular operation to every element of the array, you can use array mathematics. And these are simply other symbols. The star symbol is an array mathematic operator in NumPy. The star symbol is an array mathematic operator. And the cosine function in NumPy is an array operation. Let's look up NumPy cosine, by the way. Let's look up NumPy cosine and see what we find. Google's AI gives me a nice definition of it, but it also refers me to the manual where I can find the definition of numpy.cosine. Numpy.cosine takes an array-like input operator, which is the input array in radians, and then it specifies whether the out should be stored in a predefined array, or if not, it creates a new array and returns it. And then there are some other optional arguments that you can specify if you want. All right. I mentioned here that NumPy has this special constant, np.pi. NumPy has number of other special constants that are extremely useful if you want to do linear algebra or array operations quickly. So one of them is NumPy zeros, one is the all ones matrix, one is the identity matrix, one is the integer range. A range is the range between 2 and 6, not including 6. And one of them that's very useful is the linspace operator, which spaces from 0 to 1 in 6 steps. So let me run these, and we see that, first of all, Z is a 3 by 3 matrix of all zeros. So this np.zeros, the argument, notice, is a tuple, and this tuple specifies the size. If I want just a vector of three zeros in a row, I can specify just an integer, and it will give me a 0, 0, 0, 0. Or I can actually create a three-dimensional array, an array that has two matrices, each of which is 3 by 3. Right? So here Z is now two matrices, each of which is a 3 by 3 matrix. And I've done that by specifying that I want a tuple whose size is 2, 3, 3. So now it's a 2 by 3 by 3 array of all zeros. Similar things can be done to all of the other special commands listed here. The ones function generates a function of an array of all ones. So here, this function, this matrix O is a 3 by 3 matrix that contains all ones. The I function requires only a single integer because it creates an array that's in this case 3 by 3 and has ones on the main diagonal and zeros everywhere else. Let's look that up. So the I function creates a square matrix, a 2D array with ones on the diagonal and zeros elsewhere. N specifies the number of rows. M specifies the number of columns, which can be different from the number of rows, but if not specified, then it defaults to none. So if we want to, we can specify the number of columns here. Let's say we want 5 columns. Uh, well, that didn't work. That's interesting. Maybe they eliminated that, or maybe M has to be less than or equal to. Oh, there. No, there it is. So now I have a 3 by 2 matrix. If I specify M is 5, it should create a 3 by 5 matrix. So it's possible to create an identity matrix which is not square, but the default operation is to simply make it square, to simply make it a 3 by 3 matrix with ones on the main diagonal. The arange operator does the same thing as the range function that we used in the for loops. Remember, in the for loops, we used range of 2 comma 6 to specify all of the numbers between 2 and 6, not including 6. The NumPy arange function creates exactly the same list of numbers and then turns it into a NumPy array so that you can do operators on it. So for example, we could print r multiplied by the cosine of r multiplied by pi. And then let's take numpy cosine, numpy pi times r. And we find that the cosine of 2, 3, 4, 5 multiplied by pi is 1 minus 1, 1 minus 1, because the cosine of 2 pi is 1, the cosine of 3 pi is minus 1, the cosine of 4 pi is 1, and the cosine of 5 pi is minus 1. And then finally, the linspace function allows us to create an array whose elements are not integers. In this case, we want 6 numbers between 0 and 1, including both 0 and 1, and uniformly spaced. So 0, 0 0.2, 0 0.4, 0 0.6, 0 0.8, and 1. That's a total of 6 elements. I shouldn't say 6 steps, contains 6 numbers linearly spaced 0 through 1 inclusive, right? So that's 6 different numbers, including the 2 endpoint numbers, 0 and 1. So it's 5 steps, but 6 numbers. Let's look up that function. NumPy linspace. That one is going to be very useful for us in plotting because it will help us to create the abscissa, the horizontal axis in plotting. So we specify the start, the stop, the number of elements. Endpoint is true by default. If you specify endpoint is false, then it only generates all of the elements except for the last one. So here, if I specify endpoint equals false, then it will return a list of, and let me get rid of this. It will return a list of 6 numbers between 0 and 1, but not including the number 1. So you see we have 0 and then 1/6, 2/6, 3/6, 4/6, and 5/6, but not including 1. In that case, if I want the same numbers, maybe I only want 5 steps. 0, 0.2 to 0.8 contains only 5 numbers, not including the endpoint 1. If I go back to the default endpoint is true and specify that I want 6 numbers, then I get all 6 numbers, including both 0 and 1. This linspace is going to be extremely useful to us when we want to create plots that show both the x-axis and the y-axis. All right, now let's look at plotting. Now we have the basics of NumPy, and so let's use Matplotlib. If you don't have Matplotlib, then you can get it by typing pip install Matplotlib. But if you've installed Anaconda, then you should already have it. You can test by typing import Matplotlib. Just as with NumPy, we're going to use Matplotlib a lot. Almost everything we do will create an output, which is a plot rather than a printout. And in order to make that convenient, we can take the pyplot subfunctions of Matplotlib and output them as PLT. So this takes the module Matplotlib, its submodule pyplot, and abbreviates it as PLT. There's many ways actually to create a figure. I recommend the following technique. I recommend creating the figure first, because that allows you to specify how large the figure should be. In this fig size, the first number is the width, and the second number is the height. And these are arbitrary units. These are something like, actually, I don't know what units these are. These are arbitrary units. It's 14 units wide and 4 units tall, whatever those units happen to be. They look like they might be inches. They look larger than centimeters. All right, once you've created the figure, then inside that figure, you can create subplots by typing f.subplots. If we look this up, if we look up matplotlib subplots, we'll find that there are many, many different ways of getting subplots. So one of the ways of getting subplots is to actually type matplotlib pyplot subplots, in which case you have to specify the number of rows and the number of columns. Often, if it exists in matplotlib, then it will also exist as a function of the figure. So here I've created a figure object. Let me just print. F is an object of type, and then let me type type of F. And we'll see that F is now an object of type matplotlib figure. Matplotlib figure figure. We can find out more about matplotlib figures by searching for matplotlib figure. And yeah, here we go, matplotlib.figure. This is the general type of object called a figure. There's also the subfigure type of object. So all of that information is available online. A figure has this method called subplots, which is exactly the same as the pyplot plot. And in this case, what it does is it creates a 2x2 array of subplots. So S of 0, 0 is this top subplot. S of 0, 1 is this subplot. S of 1, 0 is the bottom left subplot. And S of 1, 1 is the bottom right subplot. And you can see that here I plotted 1, 1, 1, 1 as a function of 1, 2, 3, 4, 5. So I have 1, 2, 3, 4, 5. And as a function of those integers, I've plotted an array of all ones. Notice here I'm not plotting arrays, I'm plotting lists. This is actually the list 1, 1, 1, 1. If I convert it to an array, that's fine. Matplotlib will assume that it's something like a NumPy array, but if it's a list, that's just fine. Matplotlib doesn't care whether it's a list or an array or even a tuple. I think I could actually make this a tuple. Let's find out. Let me convert this from an array into a tuple. I think if I run that, it will still be fine. Yeah, it doesn't care whether its argument is a tuple or a list or an array, as long as it's all numerical. In this next plot, notice that I've plotted as a function of 1, 2, 3, 4, 5, I've plotted 1, minus 1, 1, minus 1, 1. In this bottom left plot, notice that as a function of 1, 2, 3, 4, 5, I've plotted 1, 2, 3, 4, 5. So here on the x-axis, I have 1, 2, 3, 4, 5. On the y-axis, I have 1, 2, 3, 4, 5. And then in the bottom right plot, as a function of 1, 2, 3, 4, 5, I've plotted minus 1, minus 2, minus 3, minus 4, and minus 5. So we can create different plots in each of the subplots, and that can allow us to often debug our processing so that we better understand what the content of an array is, right? Printing out, up here I printed out all of these arrays. Printing out the array is possible, but if your array is very large, that can be very difficult to work with. And so rather than always printing out our array, often it will be more useful to try to visualize it using matplotlib. So notice that if you give the plot function 2 arguments, it assumes that they're the x and y of one line. If you give it 4 arguments, it will actually assume that you have 2 different lines. So here I have 0, 1, 2, here I have plot as a function of 0, 1, 2, 3, 4, 5, 6, plot the cosine of 0, 1, 2, 3, 4, 5, 6. And then, as a function of 0, 1, 2, 3, 4, 5, 6, plot the sine of 0, 1, 2, 3, 4, 5, 6. And so here I have, in the blue, I have the cosine of 0, 1, 2, 3, 4, 5, 6. And in orange, I have the sine of 0, 1, 2, 3, 4, 5, 6. Notice that pi is just a little bit more than 3, and so pi is where it crosses the axis. Often you don't want just the plot. Often, especially if you're creating a written report, you might want a title and a label. So we can create a title by using the set title function. If here I've created a single subplot, and I'm going to give it the title, sine, and cosine. and the X label theta in radians at the bottom, and the Y label sine theta and cosine theta. And then I'm going to plot, and I'm going to even create a legend. And the legend for this particular subplot will include as many arguments, here cosine and sine, as were specified in the plot. So here I called the plot function with 4 arguments. Theta is the x-axis for one line, and cosine is the y-axis. Theta is the x-axis for the second line, and sine is the y-axis. Since I have 2 different lines in this plot, when I call s.legend, it creates a legend showing those 2 different lines. Notice that here I've created theta to be an array between 0 and pi with 100 steps. So now I don't really want to print that out. Why don't I print that out and see just how big it is? I'll print out theta and we'll see that it's actually quite large. It's very cumbersome to actually print out all of the values of theta. It's much more interesting to show the plot so that we can see what it looks like rather than printing out all of those values. So let me comment that out and I'll just print the plot. I can add those to subplots like these. So in each of these subplots, I could create a title. S of 0, 0, set title. And S of 0, 1, set title. And here in S of 1, 0, I'll set the title. And here in S of 1, 1, I'll set the title. And let me run this. And we see that now each of the subplots has its own title, 0, 0, 0, 1, 1, 0, and 1, 1. Notice this terrible thing happened. The title overlapped with the x-axis of the plot above it. And we can avoid that if we specify in the figure that the layout should be tight. I think this is the right way to do this. Let's find out. So if I specify when I create the figure that I want a tight layout, that will force it to take all of the subplots and shift them a little bit so that the title is visible. I don't know why they call this a tight layout, but that's what it's called. So when I create the figure, if I specify that its layout is tight, then before that figure is displayed, it will shift the title down so that the title is not overlapping with the x-axis above it. So that all of the plots kind of match up one against the other without overlapping. All right. So that's the basics of how to create plots and how to set their title and how also to set their X label and their Y label and their legend. And now 2 more kinds of plots that I want you to know about are scatter plots and stem plots. So a scatter plot is something like this, where we just have dots. If we go back to the plot types, a scatter plot is something that looks like this. It's just a collection of dots, a collection of XY dots that can be anywhere in the space. They don't have to be all in a row, they can be absolutely anywhere. A stem plot is something that looks like this. It's a plot where each of the dots has to be in a row, and there's this lollipop sticking up, right? There's this stem that connects that dot to the x-axis. So whatever the x-axis is, there's a stem that connects it. And these 2 plots are really useful for speech and for audio. Right? A scatter plot is useful for almost any kind of data. A stem plot like this is especially useful when you're trying to plot a signal that you can listen to, because this will show us how these samples are sequenced in time. It shows us that the sine are these blue dots, and the sine function rises up and then comes back down again. The cosine, which are the red dots, start out high and then go down low. All of that information is contained in the scatter plot, but the stem plot kind of makes it more obvious exactly what the numerical values are. It shows us that the numerical values are positive here and negative here. And that can be very important. Right here, it's not so obvious that this is a positive number and this is a negative number. And it's not obvious that all of these are positive numbers. You have to look over here and see, oh, 0 is at this point. And if 0 is at this point, that means that these are positive. With the stem plot, that information is immediately visible. You can immediately see that all of these are positive values. Unfortunately, the scatter plot is much easier to produce. The stem plot is a little bit more complicated. So the scatter plot is produced almost exactly the same way as the original plot. You remember that with the original plot, we specified s dot plot, and then we specified theta, and then the cosine, and then we specified theta, and then the sine. Let me show you those things. If I go up here, I specified theta, and then the cosine, and then I specified theta, and then the sine. In order to create a scatter plot, I give one more argument per line. In this case, I'm going to specify that I want blue x's for the cosine, and I want red circles for the sine. Right, so these blue x's show up as the cosine because I specified blue here and x. If I want green x's, I could change this to a green. And then I want red circles. If I want red asterisks, I could change this to an asterisk. And then if I run this, we see now that the sine is using red asterisks and the cosine is using green x's. So the first letter here specifies the color and the second letter specifies the symbol. Let me see. I'm not sure if this will give us details on exactly what those different figures are. C equals colors, V min, V max. This is using the scatter function. This is using a different function called scatter. I think these are called markers. Matplotlib marker symbols. All right, here are the different markers that are available. You can use dot to create a point, comma to use a single pixel, O to use a circle, downward V to create a downward triangle, upward caret to create an upward triangle, less than to create a leftward triangle, rightward to create a rightward triangle. This three-way symbol is the number 1. This other three-way symbol is the number 2. You can create an octagon or a pentagon or a plus sign. Let's try some of these. Let's create hexagons and let's create this 23 shaped symbol. So let me create that 3-point symbol in green, and let me create red hexagons. There we go. Now I have red hexagons and 3-point symbols in green. Let's also look up the Matplotlib marker colors. The basic colors are blue, green, red, cyan, magenta, yellow, black, and white. You can specify other colors besides those, but it's a little bit more complicated. These, the three basic colors, red, green, and blue, and the three subtractive colors and the three additive colors, cyan, magenta, and yellow, are the easiest to create. Let's try cyan and magenta in case you haven't seen what those are. So let's create the cosine in cyan and the sine in magenta. And we see that cyan is kind of a blue-green color, and magenta is kind of a pinkish purple color. So those are kind of nice. And we can also create yellow hexagons if we want to by using the Y letter. And then we find that yellow hexagons are kind of a greenish yellow actually on my screen. All right, so here's cosines and sines. The stem plot is a little bit more complicated. For a stem plot, you can only do one line at a time. You can't do, if I try to do theta comma sine comma b, then it will tell me that that's not possible. Unless they've changed it. Yeah, that's not possible. So the stem function in Matplotlib requires only one line at a time, and it only allows you to specify R. If I try to specify the marker shape, I think that will also cause an error. Oh, it just ignored it. It just completely ignored my specification of the marker shape, and instead it created a circle. So the stem plot always creates a circle. You can specify the color, so I could change this to green, for example, but you can't specify the marker shape. The marker shape is always a circle. And you can only specify one line at a time. Fortunately, the subplot keeps track of what these stems are so that when I ask for a legend, if I specify that the things I want the legend for are the cosine and the sine, then you can see that these things show up over here. Printed the cosine and the sine. I've specified that I want font size 18, and so that it created font size 18 according to some scaling. Maybe these are centimeters and it's just scaled up because these seem much larger than 18 point. But in any case, now I've created a figure that's of size 14 by 4. I've created a 1 by 1 array of subplots, that is just one subplot. I've plotted the cosine versus the theta, the sine versus theta, and I've created a title, a label, an X label, a Y label, and a legend. That's all I wanted to cover today. I wanted to make sure that you understand mathematical computations using NumPy and stem plots and plots and scatter plots using Matplotlib. The homework involves 3 different functions. I think it's 3 using NumPy. So in homework5.py, you'll calculate the center of gravity of a vector x. Let's look up center of gravity. Center of mass. The center of mass of an object is the point on which you could balance it. So see, you notice this little wooden bird figure, this toy is a piece of wood that has a long tail, a long thin tail, and a thick front body. And so the center of gravity is the point on which you can balance. And that center of gravity can be created using the following calculation. If x are the set of masses, so if we have a set of masses, small mass, small mass, small mass, small mass, small mass, large mass, then the center of gravity is 0 times x0 plus 1 times x1 plus 2 times x2, all the way up to n times xn, divided by the sum of all of the x's. These are all of the masses. If I take each of those masses and multiply by its position, and then divide by the sum of those masses, then I get a specification of the centers. So if I take, for example, x is 1, 2, 3, 2, 1, the center of mass is on the third element, which is element number 2, right? And so basically I want to take this array, 0, 1, 2, 3, etc., and take its dot product with the x vector. So let's try that using the dot product. First of all, if I run this as it is, it says 0, so that's because I haven't written it. Let's change this line. Let's say that the n is equal to the range of length equal to the length of x. And let's say that c is equal to the dot product between n and x divided by the sum of x. And let's return that value of c. Save the Python file. So here I've created an array, 0, 1, 2, 3, 4, 5, up to the length of x. And then I've taken the dot product between that array and x, and I divide by the sum of all of the masses. And if that worked, if I reload homework 5 and run it, I should get that the center of gravity of this array is the point 2. By the way, if I decrease one of these earlier elements, the center of mass should now move a little bit to the right. And if I say 1, 1, 3, 2, 1, then the center of mass should be a little bit larger than 2.0. Let's find out. Now it's 2.125. So this is kind of like that bird toy. I've created a long set of thin elements here and then a much thicker element up here, and that caused the center of mass to move somewhat to the right. Homework problem 5.2 is creating an identity matrix. This is just taking in a vector, x, and creating an identity matrix which has a size equal to the size of that vector. So if x is an input that has 5 elements, then the result should be an identity matrix with 5 elements. Well, this is pretty straightforward. This is just taking the length of x. So let me say n is equal to the length of x. And then I should just be the NumPy identity matrix. And then I should return that. So now I'm finding the length of x, and then I'm creating an identity matrix that has the same number of rows and columns as that input vector. So I fed in 1, 2, 3, 2, 1, and I get out a 5 by 5 identity matrix. And then finally, I'm going to create the sine and the cosine that we used in order to plot in this stem plot. I'm not going to ask you to put the plot itself inside of the homework because this homework is an external Python file, right? It's better to actually create the array T and the array X and the array Y such that when we take those and plot them, right? Where are we? I'm going to take those and plot them. The result should be a plot that has the cosine and the sine. So if I run this as it is, the function, my function sine and cosine is just returning a bunch of zeros. So I get 0, 0 for the cosine and 0, 0 for the sine, and that's not very interesting. What I want instead is a time axis t that starts at time t start, ends at time t end, and has this many steps. So this is the linspace function, right? I want to create t is equal to numpy linspace with a start time of t start and an end time of t end, and with t steps. All right, I have not yet changed x and 0, and if I run it like this, I'll probably get an error because I'm returning a t function that has 20 steps, but the cosine and the sine will still have 0 steps. Yeah, see, now we have an error because theta is 20 steps long, but cosine and sine are each 0 steps long. Let's take a look and see what the cosine and the sine should be. X should be an array of length t steps, which is just the cosine of t. All right, that's easy enough. That's just the cosine of t. And y should be an array of length t steps, which is just the sine of t. So that's just the sine of t. So if I save this, it's a linspace from t start to t end, and it's cosine and it's sine. Now if I run this code, I should get a plot of the cosine and the sine. All right, if you want to check that yours works, you can run the grade.py function that I've attached. You can actually take a look at this code if you want. Grade.py simply runs some test code to make sure that yours work. Test center of gravity, test matched identity, test sine and cosine. It runs some unit tests in order to make sure that your code works. And I run it here and I see it's okay. So knowing that it's okay, now I can upload it to GitHub. So now let's go to GitHub Desktop. And if I open GitHub Desktop, I should be able to check in the changes. So first of all, I want to check in the changes. So I want to commit those two files, and then having committed them, now I need to push them back to my account on github.com. No local changes? Okay, now it's pushed. All right, now I should be able to go to my account on github.com, and I should be able to see that that's actually done. I'll check into J. Hasegawa student, 2025 spring, lecture 5. And if I go to homework5.py, I can see that here's the dot product that I just wrote. Here's the identity matrix that I just wrote. And here's the linspace that I just wrote. So I can copy this URL and I can go to this week's homework. And let's make this visible to students. Now it's visible. Now this should be visible to you. So you can go to homework 5 and enter the URL of your copy of homework5.py or lecture5notebook.ipynb. Notice that the due date for every homework is July 31st. Many of you still haven't done homeworks 1, 2, 3, and 4. If you haven't, please start doing them. We have new homework every week, and the further behind you get, the harder it becomes to catch up. So please do go ahead and start working on homeworks 1, 2, 3, and 4, and also work on homework 5 this week. Thank you. So let's go ahead and take attendance now. Let me go to Campus Plan web menu. Okay, please go ahead and register your attendance using this number. Okay, we have 3 people done. The other 8 of you, please go ahead and register your attendance. That's 6 people done. The other 5 of you, please register your attendance. Counting down. Now we have 8 people done. I think that means there are 3 more of you. Please go ahead and register your attendance. Are there any more people here? It says here 8 people have registered attendance, but the Zoom call is claiming that there are 11 of you online. Let's see if I can find out how many we have. Now we're up to 9 people who have registered. Let's see. Let me end recording.